Hey everybody, welcome back to the meta career questions. Let's get started. So I had two problems remaining. This is one that I solved, and now I have one remaining. So this one is called rotary lock. Let's take a look at what it looks like. Rotary lock. Um, so so you have you're given a sequence of, I gotta switch the pen. You're given a sequence of lock numbers. For example, 9, 4, 4, 8. And also an N. So let me show you what it looks like. So you have two locks. Here's one lock, and then here's another lock. And they go from 1 all the way to N in a circle. 1, 2, 3, 4, dot, 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 all the way to, in this case, 10. And then like this. Yeah. And then the same thing with the other one. 1, 2, dot, 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 all the way to 10 on the other side. So you're given this sequence of numbers, and you're supposed to kind of in turn, you have to go through the entire sequence of numbers and go through so you have to input the numbers into the locks. So what I mean by this is you got a 9. What does this mean? You have to set one of the locks to 9. Just one of them. Set one, move this over, set one lock to position 9. Then you get a 4. Set one lock to position 4. It doesn't have to be the same one that you set to 9. Position 4, and then etc. So the objective of this task is to find the minimum number of, technically it's seconds, but minimum number of sort of movements to input the sequence. So looking at the example, you could just try to, so for example, strategy 1 would be to input entire sequence using just one lock. So you don't use both locks, you just use one lock. Entire sequence using one lock. So the way I write this is, here we start with 1, 1. So both locks start at position 1, 1. So you're just going to use one lock. So after the first one, you move one of them to 1, 9. Then since you're only still using the same one, you move that one back to 4. And then you move then you keep it at 4 because it's 4 again, and then you move the 1, 4, not the arrow, and then there's an arrow, and then finally you move it to 1, 8. So the number of movements required to input the sequence. So first we had to move 1 to 9. So the distance here is 2. You can see it's not 8. It's just it will take less time to move it this way. So that's the way we go. So this requires 2 movements. Then to bring it back to 4 here, that requires 1, 2, 3, 4, 5 movements. So plus 5, and then we keep it at 4, so that's plus 0, and then we move it to 8, which is 4. So this in total requires 11 movements. Okay. However, if we were to use both locks instead, you can notice that we can save a lot by moving one of them to 9. If we move one of them to 9 and move the other one to 4, then eventually when we get back to this 8, instead of having to go from 4 to 8, we will only have to go from 9 to 8, which saves a lot of time. And also it is also cheaper to move the other lock from 1 to 4 than the first lock that you moved to 9 from 9 to 4. So what does that look like? That looks like this. So 1, 1, so we still have to move one of them to 1, 9. And now we move the second one to 4 instead. And then we stay at 4 because we get a 4 again. And then finally, we move the one that was already on 9 to 8. So what does this look like? So this costs 2 again. This costs 3 this time because we're moving the 1 to the 4. This one costs 0 because the 4 stays. And finally, we're moving this one just 1. So this is 6, which is way better than 11. So you can see we found a much better strategy by keeping locks around where we're going to need them in the future, right? Makes sense? So how do we go about solving this problem? So let me define, so this is another kind of dynamic programming problem. So let me define the objective that we're trying to solve. So I will say, what do I call it? Let's say cost of I is equal to the minimum movements. Well, technically, okay. So this is going to change every single dynamic programming iteration. So let's say given that we are at let's see, what do I use? Is it J? Do I use J? I use a variable end. So given that we are at, let's just say J, the cost of I is the, okay, actually let me first go into sort of understanding why this might work. So let's just say we're trying to look at all the possibilities for ending up at well, actually, okay, let me see. So yeah, let's look at all the possible ways that you can get. So imagine we have a sequence of blocks, x1, or combinations x1, x2, dot, 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 to xn. So how, from which, I'm trying to think, right? From which position can we end up? I'm trying to look at all the possible moves. From which position can we possibly end up at xn? This one. So how can we get to xn? Well, we have to get from, so obviously if we're at xn, we just, we're at xn minus 1, right? So one of the locks has to be set to xn minus 1. As for the other lock can be set to any of these previous numbers. So xi for any I here, or even 1. Because we could have left the lock at 1, at position 1, and just moved the second one all the way through all of these x's. In which case, we would still have a lock on position 1. So all the possibilities are xi, so for every single I, xi, so these are the possibilities where we might have just come from. For all I, xi, or 1. Okay? Makes sense so far? So then, given that we know these possibilities, we can try to, so these are all the possible places that we need to look at when trying to find the minimum number of movements to get to get through all the sequence, including xn. So I'm trying to find a way to get through all the sequence and xn. And we can do so by, these are all the possibilities. So now, how many movements does this require? Well, this requires moving from 1. So this one you kept it at 1, right? So this requires moving 1 to x1 to x2 dot 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 to xn minus 1, and finally to xn, right? That's the cost of doing this one. As for the cost of doing this one, so if we have 1 at xi, what this means is that we were able to do whatever correct sequence of moves until we get to xi, the optimal sequence of moves to get to xi. And then after that, since we kept 1 at xi, we decided to only move the second lock all the way to xn minus 1. So what does this mean? This means that we don't know what sequence of moves we did, but we finally got to xi and then something else. And then after this, we were able to move this question mark to x this to xi plus 1, and then to xi plus 2 plus dot 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 to xn minus 1, and then finally so, I mean, in order to maintain an invariant, we will have to, so the question is, okay, so let's just say we got to this point, xi, xn minus 1. So which one do we move then? Do we move the xi to xn, or do we move the xn minus 1 to xn? Like, so there's two possibilities. So do we move the lock that was just at the previous number, or do we move the lock that we have been saving up all this time, right? Makes sense? So in order to make this more straightforward, let's just try to define an understanding of what exactly we're looking for. So given that we are at, I guess xn is what I use here, given that we are at n, the cost of I is equal to the minimum number of movements of movements. Let me think. So we're trying to get to get to xi by whichever means necessary. Whichever means necessary. And then move the other lock all the way to, I think this will be all the way to xn. So we're never touching this xi again. Why? Because this xi is tied to this I. So this is the cost of I. So we're never going to touch this xi. But we're going to move the other one all the way to xn. So this is a valid movement pattern. So it's going to get us through all the x. It's going to get us through all the xi's, and yeah, very straightforward. So yeah, so let's look at how this can help us. So I guess, yeah, so if we are at n, we have this cost of I, and now in order to find out the minimum number of in order to find cost of n, is what I'm saying, we're going to look through all of these possibilities. So we're going to look at, so I'm basically, I know it's kind of confusing, cost n minus 1 of I plus the distance between the n minus 1, so the combination, so x n minus 1 and x n. I think that's right. Yeah, I think that's right. So what does this mean? Cost n minus 1, I know this is super confusing, but like this is a dynamic programming problem, which means in order to be most efficient, it builds upon itself and it replaces the results from the previous one. So let me try to take a look at an example, because I mean even the example is sort of difficult to understand. So 9448, so we also have to, so in order to make this computation easier, I added a -1 to the beginning. So okay, so here's my dictionary. So this will be the cost dictionary will be a dictionary, and this will be a map between I and a cost. So we fill it initially with -1, and then probably the distance between x0 minus 1, or the distance, not necessarily subtraction, distance between x0 and -1. Okay, so now in step 0 of this dynamic programming problem, we're going to look at, we're going to try to evaluate what's the cost of 0. Cost of 0, I think, yeah. So what is the cost of 0? This is the minimum movements to get to x0 by whichever means necessary, and then have the other lock all the way to xn. So this is, so since we're at step 0, right, this is honestly the optimal way to solve so far. And I mean, it's very clear what to do. You just have one lock, right? You only have one choice, and it's to move the either one of the locks to position 9, right? So step 0, cost 0. This is the minimum movements. This will be equal to 2, right? So let's try to write it in terms of our formula here. So this is cost of n minus 1 of I. So also this is, yeah, I forgot to say this is the minimum across all i's. Across I and I. Yeah, that's right. So we only have one I. This is this -1, which is the lock's state in the beginning where they're both set to 1. So the cost of 0 is equal to the cost. I think, I don't know, did I really set this to, I guess I did, right? You see that? This is C0 minus 1. I think maybe, yeah, I think maybe I did it a little bit more. I think I started, what I did, I think, in order to make, I don't know if it made the math simpler, but I started with with evaluating cost of 1, because I think, did I already evaluate? No. I mean, I just like looked a step ahead instead. So the cost of 1 is the minimum number of movements to get to x1. So we get to 9 and the 4. So we already know what this is. The best sequence of movements is we move 1 to 9 because we have to, and then we move the other one to 4 because it's less expensive than moving the one from 9 back to 4, right? So we're going to look at, wow, this is kind of complicated to explain. Yeah, like, let's reread the definition again. Minimum number of movements to get to xi by whichever means necessary, and then move the other lock all the way to xn. So, because we're going to look through all the different possibilities. So, what are the different possibilities? Okay, let's just take a look. What are the different possibilities to get to 9,4? Well, either we are at 9. Well, there's only one possibility, 9,1, right? There's no other possibility. We keep the 1. We have to keep the 1, and then we have the other one at 9. So we're looking at the only possible possibility, which is this 9,1. And we try to move the other one to 4. Yeah. So this isn't 2, this is 5, actually. Yeah, the other thing I wanted to say was that not only do we need to replace, so this cost array I'm keeping over every single step that I do, over every single new pattern that I look at, and obviously the number of movements required keeps increasing. So not only do you need to, so this thing is like an update. So look, so when you update the minimum number of movements to get to xi, so for when you're at step n, right, then this is optimal, right? Minimum movements to get to xn. However, and then move all the other ways necessary, because when you get to xi, and then move the other lock. So this part is optimal, right? Minimum movement by whichever means necessary. This is very optimal. However, this second step, which is move the other lock all the way, this is not optimal at all. However, if we are at xn, then cost of n is just this first part, because the other lock is we've already touched xn. So this will be the optimal strategy, given that we don't know, like if we're at step n and we calculate cost n, that is the optimal strategy to get to xn, right? But we don't think about the future locks, right? So what I'm trying to say is that we update this. So we look through every single of these possibilities, these xi. So we do a loop over for xi in 1, and then x1 dot 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 to x n minus 1. We do a loop like this, and then we set cost I. So we set cost n to the minimum of this thing that we just calculated. So the previous value of cost n minus 1. So what is cost n minus 1? It's the minimum number of movements to get to x n minus 1. To get to xi, it's cost n minus 1 of I. So it's the minimum number of movements. It's like the previous value. Minimum number of movements to get to xi. We're still getting to xi, and then we're only moving to xn minus 1, right? So then in order to update this, sorry. did I write? I think I meant this. This is the one I'm currently talking about right now. So in order to update cost of I, this is equal to cost of the previous cost of I plus the distance between xn minus 1 and xn. So this was by definition, this is the minimum movements to get to xi, right? And then move all the lock all the way to xn minus 1. And now we want to update it, so it's cost of n for the nth iteration. So this is for iteration, and iteration is currently n, this dynamic programming iteration. So we're updating this value from I by adding the not optimal thing of moving the last lock. So we fixed the lock to that it only gets to I, the one that we want to get to I, and then finally the second lock we have to move it one step further from xn1 to xn. Hopefully that makes sense. Why do we need to update it? We just do. Yeah, we just do, because that's the way we define this definition. So we're going to use this cost n minus 1 times I, right? So how do we evaluate this cost of n? Cost n of n. We evaluate it by this plus the distance. This will be, is it the minimum distance? No. So we don't care about, well, actually we do care about this was something which tripped me up. So what is the definition of this cost n of n? Is the minimum movements to get to xi, to get to xn by whichever means necessary, and then move the other lock all the way. And it's actually this, not exactly whichever means necessary. So the requirement in order to be defined as cost of I is that we end up with one lock at I. End up with one lock still at I. So we can reuse the value, so we can reuse this computation in the future. When we look at all the possibilities, right, this is the point. We're trying to reuse the computation. When we look in the future at the previous possibilities, we're trying to look through all the possible values, and the possible values are, okay, we stopped at I, and then we moved only the other lock forward. So we have to remember to stop at I with one of the locks. So when we do this cost of n, we the idea is that we moved one, we got to xn by whichever means necessary, but then we can't move the lock from xn because we're trying to reuse this computation in the future. We can only move the lock from the previous value. So this will be the whatever xi to xn. Make sense? And so this is minimum. We're doing this over all the possibilities of xi. So we're going to take the minimum with itself so that we get the smallest possible value. So this is pretty much our solution right here. So for iteration, where this so this is from n equals 0 to probably n minus 1. I think it's n minus 1. We're going to look through all the possibilities, and then we're going to have to update not only our cost I, but also our, I don't know if this happens before, I think, well, it doesn't matter. It happens at the same time. Like we need this value to, we can't overwrite this value. So, I mean, it would be intelligent to do it this way, in this order. So we don't overwrite it. But yeah, we not only do we need to update this cost n with we're looking through all the possibilities, but we're also updating this cost I with a new distance because we're looking at a new iteration. So this should be cost n of I. I mean, I'm going to overwrite it because we don't need the previous values, but you could just as easily save it and then just put it into cost n of I. So what is this cost n of I? This is, here, let me put this here. Minimum movements to get to xi by whichever means necessary, and then move all the way to xn. So it has two parameters, this definition. Make sense? And it just so happens in my solution that I overwrite the cost n minus 1 of I. I overwrite it with over right with cost. Let me make sure I'm still recording. Yes, I am. With cost NOI. So yeah, hopefully that makes some sense. So let's take a look at what the code looks like. I think, so I was getting confused a lot. You actually don't need two arrays here. They actually ended up doing the exact same thing. So every time you see this second array, it's useless. So there we go. And then I also, the thing is that the return, so this, when you try to return the final value of the correct value, of this computation, unfortunately your cost of n of I, specifically your cost n in the final round, it assumes that you moved the lock x n minus 1, assumes you moved it, you weren't allowed to use xn minus 1, you weren't allowed. What you were allowed instead, because that's what, or technically by our definition, I'm not sure. I think I'm getting confused the xn minus 1, but yeah. Yeah, I think, yeah, because we're trying to touch xn minus 1. Did I say xn minus 1? To xn, cost n minus 1. Where's the not allowed? We end up with one lock still at I. Yeah, okay, fine. So we weren't allowed to move xn minus 1 because the definition of this, cost n, we still have cost n, I guess this should be n minus 1 technically. Yeah, n minus 1. So we weren't allowed to touch xn minus 1. Because otherwise it would have ruined our invariant. So instead, we have to keep track of a return value that just for the very last iteration finds the distance between the the minimum. Sorry, it finds the minimum so the minimum between the distance of the one that you have been saving up all this time. So xi xn and distance between xn minus 1 and xn. Because for the final iteration, you don't really care which one of these do you move, the xi, which you have been saving all this time, or the xn minus 1, which is the one right before xn. You don't really care on the last iteration. Therefore, you choose whichever one is best. And if you don't choose whichever one is best, and you choose automatically as xi, then you might get the wrong answer. So that's the way it works. That's the way that works. So that's why I do this minimum. So here's the minimum that I told you, where here I replace cost from I with something that comes from cost of I, and then here I replace, or I try to find the minimum one by minimizing with itself. Yeah, I think, and then here's my distance function, also important because we do need to find a good way to measure the distance between two targets. And if not only do we need to measure the distance from target to source, but also if we go the other way on the lock, right? That's we're trying to find the either distance works for us, and we need to try consider only the minimum distance. So yeah, so that's it. This was a difficult problem. Thank you very much for listening. I'll see you next time.